In our last video, we said there would be one more method that we had for studying limits of sequences that is a new tool that we did not have for studying limits of functions. And that's what we're going to look at in this video. So the object we're going to look at here, or the theorem we're going to look at here, is the bounded monotonic sequence theorem. And this is going to be something a little new because it's not like what we've seen before for functions. But to develop it, we need to build some vocabulary. So the first thing we're going to say is a sequence is non-decreasing if each term is greater than or equal to the previous term. And so it's a sequence of numbers where the numbers are getting bigger or staying the same. So here I have an example, an is equal to n squared. A sequence is non-increasing if the terms are getting smaller or staying the same. So here I have an example that's 1 over n. Now I'm going to make a little remark here, which this is an example of something that is increasing. And this is an example of something that is decreasing. And so if you think back to Cal 1, you had this language of non-decreasing, increasing, non-increasing, decreasing, this language for functions. So hopefully these words are not new for you, and it'll ring a bell from your memories of Cal 1. Now, we're going to be interested in sequences that have one of these properties. And so we'll say that those are a monotonic sequence or a monotone sequence. Okay, and here I have these two examples that are not monotonic. And the reason for both of them is that they jump around too much. Like this an is minus 1 to the n times n. That thing is going to alternate in sign. So it's going to go up and down and up and down and up and down like a zigzag pattern. Sin n is going to be more complicated, but it's also going to wobble around and not go always up or always down. So we're only interested in sequences that go always up or always down. So now we're ready to state the theorem. The bounded monotonic sequence theorem, we suppose that we have a sequence, and we want it to have a large constant m, so that all the terms have their absolute values less than or equal to this m. So what that means is it's bounded. So if you think of, let's say, a game, right? If we're talking about how the ball is out of bounds, what that means is the ball has left the valid playing area. Well, that's the same for a sequence. We say the sequence is unbounded if it leaves any conceivable playing area. And it's bounded means we could find a giant enough court where that ball is going to stay in the court. Okay, so we suppose that we have a bounded sequence, and we suppose it's also monotonic. Then the content of the theorem is that a limit exists. And furthermore, that limit has to be bounded by the bound as well. Okay, so in practice, we don't need this absolute value condition, right? That condition is more than we need to check. So for instance, if the sequence is non-increasing, that means the values are going down. That just means that we need to find some number so that the ANs are greater than or equal to whatever, some lower bound. Let's call this one B. And if it's non-decreasing, we need to do the opposite. So that's what the bounded monotonic sequence theorem says. And this theorem, as it is, like this theorem is incredibly abstract. It's a theorem about the existence of something but it gives us no real method to find it. But surprisingly, that's going to be useful enough for us to be able to use it in applications. So let's do an application that illustrates the power of this theorem for us. In this example, we're going to consider a sequence defined by recurrence where xn plus 1 is 1/2 of the quantity xn plus 2 over xn, and we're going to start at the initial condition of x0 equals 2. Now, this problem is actually pretty subtle and is complicated enough. I would not give it to you exactly like this if I were assigning it. But what I would do instead is break it down into these steps that I'm giving us. So the first step is to check that this quantity, 1/2 times the quantity x plus 2 over x, is greater than or equal to root 2 for any positive number x. Now, that's just a calculus problem, right? So that first bit is we're going to let f of x be given by 1/2 x plus 2 over x, and we're looking at it on the interval from 0 to plus infinity. Okay, this is a nice Cal 1 review that we're doing here. And if you make a quick sketch of what this function is looking like, right, it's always helpful to have a little quick sketch here to help visualize what's going on. Well, when x goes to 0, this thing goes to plus infinity. So it's going to have a vertical asymptote at 0. And then as x goes to plus infinity, it's going to look like 1/2 x. So it's going to have an oblique asymptote. I'm not very good at drawing this, but let's try like that. It'll do something kind of like that. Let's see if I can make a smoother picture. It'll make something like this. So we see that there's going to be a critical point, maybe more than one, but there's going to be at least one critical point, and the minimum, if it exists, will be at a critical point. So let's find a critical point. Let's say f prime of x, well, that's the derivative of this thing. We get 1/2, and then here we're going to get 1 minus 2 over x squared. And when we solve f prime of x equals 0, we get 0 equals 1/2 times 1 minus 2 over x squared. So that means that 1 minus 2 over x squared equals 0. So 1 equals 2 over x squared. So x squared equals 2. So x is plus or minus root 2, but we were only looking on 0 to plus infinity, right? But we considered positive x, so x equals root 2 is the critical point. And since there's only one, that must be the minimum. Oops. Not minimum, minimum. Okay, so now let's grab us a new page and keep going. So that means, right, remember that f of x was this 1/2 times x plus 2 over x, and we said the critical point is at x equals root 2. So what do we get as the critical value at root 2? That's going to give us 1/2 times root 2 plus 2 over root 2. So that's 1/2 of root 2 plus root 2. So that's just root 2. Hence, f of x is always greater than or equal to its global minimum, which is now root 2. And then that's for all x that are positive. Okay, so that's good. But then that means, right, we had that xn plus 1 is this f of xn, and by this, that means it's greater than or equal to root 2. And we have that x0 is 2, which is greater than root 2. So all the terms in the sequence are greater than or equal to root 2, which is what we were supposed to do. Good. So now let's take a look at step 2. Right, so step 2 says, let's show that this sequence is decreasing. And really we have 2 tricks for seeing that a sequence is decreasing. One of them is to look at a ratio of subsequent terms, and the other is to look at the difference of subsequent terms. So here we look at the ratio. We're going to look at this xn plus 1 divided by xn. And that's going to give us, we're going to get, I'm distributing the xn across. So that's going to give us 1/2 times this quantity. That's 1 plus 2 over xn squared. So that's going to give us 1 over 2 plus 1 over xn squared. But we know that xn is greater than or equal to root 2. So this means that 1 over xn squared is going to be less than or equal to 1/2. So xn plus 1 over xn is less than or equal to 1. Okay, and I said here decreasing. That was a mistake. What it should be is non-increasing. And indeed, this inequality here tells us that xn plus 1 is less than or equal to xn, so it's non-increasing. And that's then step 2 of this problem. And now we're going to look to move on to step 3. And step 3 is the part of the problem where we actually end up using this fantastic bounded monotonic sequence theorem. Okay, so good. So from steps 1 and 2, we have that the terms of the sequence are trapped between root 2 and 2 for all n, and we have that the sequence is monotonic. So by our theorem, there's a limit that exists, and we're going to call it L, right? And by the theorem, that's by the theorem. And we know also that the limit is trapped between these 2 quantities. Okay, so now let's go ahead and use the recurrence. So L is the limit as n goes to infinity of the xn's. But as n goes to infinity, so does n plus 1. Sorry, as n goes to infinity, so does n plus 1. And we can now substitute the formula we have. Right, that's just because we just reindexed, basically, and reindexing doesn't change a limit. But now, by limit properties, this is equal to 1/2 times the limit of the xn's plus 2 divided by the limit of the xn's. So that's 1/2 of L plus 2 over L. Oh, not for L. Okay, so that's the this relationship now we have on the limits, and now we just solve it. This is just an algebra problem. And so this is going to be L is going to be 1/2 of L plus 1 over L. So moving the half L over to the other side, we get 1/2 L is equal to 1 over L. So that gives us that 1/2 L squared equals 1. So L squared equals 2. So L is plus or minus root 2, but we know from that underlined in red statement that root 2 is less than or equal to L is less than or equal to 2. What that then gives us is that L is equal to root 2. So that's our limit. The limit is root 2. And that was the result now of our 3-step method here. So that's an example of using the bounded monotonic sequence theorem in order to figure out limits in combination with studying things in the situation of a recurrence. Right, so that's putting the recurrence idea together with the bounded monotonic convergence theorem together. Sorry, I keep saying the theorem wrong because when I was a student, I learned it as the monotone convergence theorem. So in our book, we call it the bounded monotonic sequence theorem. Okay, good. This example that I gave you, I didn't pull it out of thin air. Instead, it actually comes from a larger class of examples, and I'm just going to throw out there, in case you're interested, what it's about. This is a special case of something called Newton's method, and that's a method for approximating roots of equations, especially of polynomials, and it's called Newton's method or the Newton-Raphson method. And if you're interested in learning more examples like this, I encourage you to take Math 464, but you'll have to take Math 353 first. But I do think it's a beautiful, beautiful area and a beautiful family of examples. Okay, that's it for this video and this application of the bounded monotone sequence theorem for finding limits. In our next video, we will look at a couple other things having to do with sequences. Specifically, we're going to start building a new class of examples called series.